Let the reaction proceed for 5 minutes. You stop it by adding DNS. We have at the benches dispense that's preset to 1 ml of DNS. You lift it up and down. It's done. It stopped the reaction. It's very alkaline, about pH 14. Any amylase that is in that tube is instantly denatured to lose activity. You then always heat greater than 95 degrees C for 7 minutes. That drives the reaction of the DNS with the reducing unit, that aldehyde, the linear form. You then cool it, add 5 mL of water so you get enough sample for the spec tube, and then transfer and measure OD. And we always want to vary only one parameter in experiment. Only one parameter. That's good experimental design. So I did this again in red because this is always true. So the assay is as follows. We have the starting substrate, which is this polymer of glucose, alpha-1,4 linkage. We take and are going to cleave it into many maltose units. So notice the net change is what here? The net change is 2. The gross change was 3 in reducing units, but the net change is 2. Why? Because this one had 1. So we have to have a blank. We have to take into account that background. All right, so that's what we'll be doing. The DNS reacts with the aldehyde when it's heated. We see the brown color. We measure it. Everyone does part 1. Everyone. All groups. You'll do this as pairs. Groups 1 through 14. Everyone does this. So you have 5 tubes. There's a blank, which means there's been no reaction with amylase. Question. So the question is, does maltose have 2 sides? So what happens is with maltose, again, only this one can go from ring to linear, because to do this one, you have to break the covalent bond there, okay? So that's different. If this goes to ring to linear, you convert the maltose into 2 glucose units, okay? So only the terminal one can do that ring to linear, okay? Does this make sense? Only the terminal one. Again, there's polarity here. So there's a 4, a 1, a 4, 1. So only this one can do it. If this one does it, you have to break that bond there to form the aldehyde, which means this is no longer linked, okay? All the way to the left. This is the only one that can do it, okay? All right, let's just move on. Okay? It is the only one that can do it. All right, if you want to discuss this individually later, but it is the only one, okay? All right. So let's move on. 5 tubes. There's a blank. There's one with 50. There's one with 100, 200, 400. So what I'll do is I'll talk to the organic chemistry professor, and maybe they can come in and describe it for you guys, okay? Would that be better? Yeah? I can do that, okay? So 50, 100, 200, 400. So 5 tubes, each like that. We're going to have 1 ml of 4% starch to each tube. So each tube will have that. Yes, question? Go for it. So I think, is that right? Okay. Net effect is the same. Only one reducing unit, okay? So it doesn't change the results. Doesn't change the interpretation, okay? All right, so let's go on. 5 tubes, 4% starch each tube. React for 5 minutes room temperature. The way you stop it is add 1 ml DNS. You have to heat all the tubes, including the blank. Why would you have to heat the blank? No reaction occurred with the, to produce the maltose, right? Why would you have to heat the blank? Because you need to have the DNS react to the background, right? And that only happens at high temperatures. So you have to heat it, okay? Then cool it and measure it. So what's your prediction? What should happen to the amount of OD or product? If you double the amount of enzyme, if you have excess substrate, what should happen to the amount of product? Nothing? I think it should change. Should double, right? If you double the amount of enzyme, the amount of product should double. As long as you have excess substrate, okay? So you expect some sort of straight line. This is what you'll do in lab. Instead of using these specs, you'll now use the new ones. Okay, so for part 2, the environmental effects of saliva. So we're various things. If you're group 1, 2, 3, or 4, you do one experiment, 5, 6, 7, another, okay? So it tells you in the lab which ones you'll do. But again, the same is always true. Always 0.5 ml of enzyme or diluted saliva. Always 1 ml of substrate. Always terminate the reaction after 5 minutes. Always heat. Always cool. Always measure, okay? So this is where the most common mistake is made in lab. So in this case, we're going to vary the temperature. So again, we're going to have 5 tubes of starch. And what we're going to do here is we're going to have 2 mils in the tube. We only use 1 ml for the reaction. But what we need to do is we're going to have the starch, since we're varying the temperature here, we'll have 2 mils of starch here. And we'll have our enzyme here. So the way we'll do the reaction is we let these sit in that temperature for about 5 minutes. That makes sure this comes to that temperature, whether it's 4 degrees or 37 or what it happens to be. This comes to that temperature. And then you'll take 1 ml out of this and add it to this. And then that starts the timing, and that stays in that environment, whatever the temperature is. For 5 minutes, you'll pull it out, add DNS at room temperature, it stops the reaction. So this allows those solutions to come to the same temperature so that when you start timing, they're there. Okay? Because if I took a tube at room temperature of starch and I added it to the enzyme and then I put it in a refrigerator, it does not instantly get to that temperature. So I have to make sure they're both at the temperature. Is that clear? So for this part, for the temperature, you have to equilibrate the 2 tubes at the different ones. You let them react for 5 minutes in that environment. You add the DNS, and then you do have to heat all the tubes again for the 7 minutes or so to drive the reaction of the DNS with the reducing unit. Does that make sense? Yes or no? Yeah? That's another one mistake that's made, is the students don't heat those tubes because they already did something with the temperature. So make sure you heat it, okay? And you have to heat the blank as well, because you have to take into account the background. So your prediction for this would be there's going to be some temperature optimum. What do you think it might be? This is from humans. So 37? Okay. That's what you might predict, but you may find something different in lab, okay? So 4 groups will be doing this, groups 1 through 4, I believe. Okay. Any questions about this? The equilibration part is a little bit more steps. Ideally, we would do blanks at every temperature, meaning you would have that starch at 4 degrees, 37, and do the blank. But these students already complain because it takes a lot longer than the other students, okay? So to do it right would be additional blanks, but it would add another half hour, so we don't do it the ideal way, okay? Is that clear? All right. One experiment is very amylose. Now, you didn't actually get this in lecture yet. KM, you never heard about Nicholas Metons and KMs, did you? No. So let's just do this. So if you plot activity here, in this case, it could be OD, it could be micromoles maltose, and concentration of amylose. What we'll see is, and this is for a constant amount of enzyme. So the one variable is the starch. Clearly, if there's none, there should be no activity. And there's a certain point where you saturate the enzyme. So additional concentrations of amylose does not yield any increased activity. So there's a Vmax, which is the maximum velocity for those conditions at a given amylose concentration. So the way you determine this graph is you take and do various concentrations of amylose and do the plot. Okay? And since it's the amylose that's the parameter that's being varied, and that has the background, you do have to do a blank for each amylose concentration. So this has to have multiple blanks. And it would be ideal if we did multiple blanks for the temperature experiment, but just there isn't enough time, okay? So the prediction for this is we should see some sort of graph like this. And in fact, there's this value called the Km, which is 1/2 Vmax. It's the substrate at which you reach 1/2 Vmax, okay? That's the Km. And different isoenzymes, salivary versus pancreatic, would have different Kms most likely, okay? All right? So is that clear? So you can talk about affinities. This enzyme here needs less substrate to reach 1/2 Vmax. So this has a higher affinity for the substrate. Takes less substrate to reach 1/2 Vmax, higher affinity for the substrate, okay? So those two are sort of inverse, okay? Higher affinity means a lower Km value. So that's probably one of the first values determined when you're studying enzymes and new enzyme is you do this sort of plot to determine the Km in affinities, okay? If you're trying to isolate various enzymes, oftentimes that's what you do. The saliva experiment, what we're trying to do here is part 1, we varied the amount of amylase, the enzyme. So we had that nice linear graph. For this part, we varied the saliva. So we're going to do various dilutions. I have to go over dilutions with you. I'm not quite sure why. I think dilutions apparently are very difficult to do. I know job recruiters who tell me that whenever they interview Berkeley students and they ask them to do dilutions, they tend to struggle with them. I'm not sure why, but they've told me they've hired students on the spot when they get the dilution correct. So let's go over how to do that, okay? I don't know why. They literally tell it to me, yeah, it's amazing. So let's just do this. Dilutions. The way we do a 1 in 10-fold dilution, you do it many different ways. But what you're going to do is you always have your original and then a diluent. So if it's a 1 in 10-fold dilution, at the end, and this occurred during office hours, you got to take into account your original volume. So if I had 0.3 mils of some solution, say X, and I want to have a 1 in 10-fold dilution, that means this has to be 3 mils, final volume, which means I have to take and add 2.7 mils of diluent, because it's going to be the original plus 0.3. So it's the starting over the final volume. All right, so if I want a 1 in 10, 0.3 starting, I know my final has to be 3, so that's 10 times as much. So to get my diluent, it's 3 minus the 0.3 to come up with 2.7. Usually what happens is people forget that they have to add that volume to it. So what we're going to do in our case to make it fast and easy for you, we have dispense that's preset to 4.5 mils. So to get a 1 in 10-fold dilution, it's half a mil. So the way you do this is you're going to spit in a cup, get a couple mils of saliva. It's going to be very foamy. It's okay. Centrifuge it. Balance the tubes. Put them opposite one another in the centrifuges. Okay. The shortest length of time we had was 5 minutes for a new centrifuge. They weren't put in balance. They got off balance and literally broke the rotor shaft. So make sure they're balanced. You're going to get a pellet. I call it oral debris. I don't know what it really is. It's oral debris. It's white. It's plaque, bacteria, pieces of Oreos. I don't know, okay? But ignore it. That's not what you want. So there's a pellet and a supernatant. Supernatant is the liquid portion. So you want to take the supernatant. Now that's undiluted saliva. So if you take half a mil of that and add it to this tube that's already got the 4.5, it's now a 1 in 10-fold dilution. Because a half a mil plus the 4.5 makes this a total of 5. That's a 1 in 10. Anyone not see that? Okay, I almost guarantee you, well, I can guarantee you there will be a dilution question on the lab exam. Okay? Every semester I've had a dilution question on there. Every semester, okay? So 1 in 10. So to get a 1 in 100, you just take half a mil of this 1 in 10 and add it to that 4.5. This is now 1 in 10, but it's 1 in 10 of that, which makes this 1 in 100. And it's in this series. Does that make sense? So it's a serial dilution. That way you just go right down the line, okay? And it turns out that the amount of enzyme activity is so high in this 1 in 100 and 1 in 1,000 that your solution will probably be jet black when you heat it up. And there's no way you can take OD on it, okay? So there will be a value here, though, that you can get a nice value in terms of the spec. Now, this experiment is identical to part 1, except part 1 you used a known amount of enzyme. So in this case, you can use it to figure out what the equivalent activity would have been, what it would correspond to. So you have a curve like this from part 1. Have you seen a standard curve like this before? Yes, the red dye was a standard curve. You figured out the concentration of it based on your OD. So the same thing's happening here. You have an OD, or micromoles maltose. You read over and down. Now that's the equivalent amylase activity. But you have to take into account the dilution factor, right? So this is 1,000-fold diluted. You have to multiply by 1,000, or if it's 10,000-fold, you have to multiply by 10,000, okay? Is that clear how that works? It turns out it's one of the more difficult ones to do. It's fairly easy to do it. It's just applying the concept of the standard curve. Any questions about standard curves? We'll use standard curves repeatedly. It's oftentimes how we do things in lab. If we want to study some unknown, we'll make a standard curve for that day. We almost always have to repeat the standard curve every day because the temperature of the room is slightly different. You may have made a solution slightly different, et cetera, et cetera. So you almost always take your standard curve over every day and then test it. The last part is the pH experiment. So remember back when we did the pH and pKa, and is this protonated or unprotonated? So clearly the pH can affect the charge state of some of those groups, right? The mean groups, the acid groups, things like that. So what we're going to do is actually just test the pH. So you make gray solutions here. And again, the variable here is pH, one parameter. Now, we do have to make multiple blanks here. It's not something you would think ahead of time that you need multiple blanks, but there is acid and base hydrolysis of starch. So this is one case. So sometimes when you design an experiment, you don't know all the things you have to take into account until you start doing the experiments. So for the pH, you do have to do multiple blanks. Although you might not have predicted that ahead of time, you do. Likewise, for the temperature one, we should do multiple blanks, but we're not going to just it takes too long, okay? So we would expect some pH optimum here. So since it's salivary amylase, what do you think the pH optimum might be? Around 7 maybe. If this was an enzyme that was functional in the stomach, what do you think the pH optimum might be? Around 2, 3, yep. So, all right. So then a couple eye clicker questions to see if you can integrate some material. You don't have to like eye clickers, okay? I'm not going to give you points. Just trying to get you to think about some of the things. Okay. So how many of you actually did this calculation for the water molecules? Not many hands. The difference between the pH and the water is that the concentration is very different, right? So in water, it's 55.5 moles per liter, not 1 times 10 minus 7, right? So that's the difference. The volume didn't change. All that changed was I asked you if it was pure water. So the concentration of water changed. The way you calculate this is a liter of water weighs 1,000 grams. A mole of water weighs 18 grams. 1,000 divided by 18 is 55.5. That's the number of moles, okay? And then you just do the math and multiply by Avogadro's number. Here's a question here that is more for the 1A exam that's coming up. Where can intact DNA be found? So which ones? Certainly C. Certainly D. ER? No. How about lysosome? So if you notice I put intact, the reason why I did this is because lysosomes are degradative organelles, so they couldn't be degrading DNA, so that's why I put the term intact. It wasn't meant to be a trick question, it was to avoid a student saying, oh wait, what about lysosome this? So sometimes if you overthink a problem and you miss a question on the exam, you can email me, explain to me your rationale, and if I buy it, I can give you credit. Okay? But typically follow this straightforward. Okay, here's an experiment. Just try to do this right now. Draw a reaction profile for an endergonic reaction. So go ahead and draw that. Endergonic, not exer, endergonic. Okay. All right, so a few more questions. Again, this is to help you with the exams to start thinking about some things. I know one of the discussion GSAs told me they had a mock exam today where they pulled some questions off the exam. So if a reaction is equilibrium, what's the delta G? 0. Forward and reverse reactions are the same. So if you had, right here, so try number 2, okay? Oh, no, don't do number 2. 2 is easy. Do number 3. Number 3 is the hard one. 2 is easy. 3. So last year students did really well in this question. Okay. So let's just do 3 answers. Okay, A, B, or C, those are the thing. A, the forward reaction is less than the 0.1. No one? Good. How about B, equal? Okay, so fair number of hands. How about C, faster? So B actually was a little bit higher than C, but C is the correct answer. So let's go over this and think about this. So the enzyme causes the reaction to go faster or slower? Faster, but since it's at equilibrium, the forward reaction is going faster, so what about the reverse? Also going faster. Okay? So the enzyme, the reason why the forward and reverse can go faster is the delta G, the energy of activation, is lower. So both the forward reaction goes forward faster, but since it's at equilibrium, the forward and reverse reactions go the same, so the reverse has to go faster. Okay? So, okay, I think we'll just end it there. Enjoy the lab.